I have a better way of making you to understand Hilbert spaces and Banach spaces. Now, if you are just coming across this channel for the first time, please subscribe to this channel, like the video, comment, and share. You can like now, then subscribe now. Thank you. So now let's dive into the major topic. One important thing that you need to understand is that whatever we are doing here, we are building on vector spaces. Now, a vector space will only allow the sum or addition and subtraction of vectors, maybe scaling. But what if you want to measure the length of a vector? What if you want to calculate the angles between two vectors? What if you want to know the distance or how far apart two vectors are? Then you need other rules. That is where the idea of norms, inner product, comes in. We are talking about norm X or norm in particular. It's talking about the length of the vector. When I say norm X, I'm talking about how big is vector X, the length of a vector X. When I'm talking about the inner product of two vectors X and Y, it's like talking about the, dot product of X and Y. Now, these both concepts of spaces gives real or complex results. Now, when you are considering a vector X, let me say x1, x2 to xn, and I'm considering another vector y, let's say y1, y2 to yn. Now, the norm of this vector x, considering this vector now, is the square root of saying x1 squared plus s2 squared plus xn squared. That is the definition of norm in the usual norm space. Now, it can also be defined in some cases. For instance, in terms of when you say Manhattan norm, that one is defined as this. The absolute value of x1 plus the absolute value of x2. So we have other norms like that. We also have a norm that is called the maximum norm, but our focus is on the usual norm. Now, when talking about this, let's talk about the inner product. The inner product is expressed as x1 y1 plus x2 y2 to xn yn. Now, this is the expression of norm and this is the expression of inner product. Now, these two, they have what they do. This one talks about majorly the length and only length of a vector. While this one compares two vectors. What does it do? What is the angle between these two vectors? This one deals with angle. Now, this one is talking about dot product as well. Are these two vectors perpendicular to each other? Then you are talking about inner product. Now, let's move to the relationship between the two. Don't forget, I defined norm S. Let's consider just these two vectors for easy explanation. I'm considering vector S and I'm going to be considering vector Y as well. Just two of them. So now, if I'm to express norm X in terms of this, I'm talking about the square root of x1 squared plus x2 squared. If I want to consider the dot product, or I say inner product of x and y, I'm talking about x1, y1 plus x2, y2. Now, let me just do something. I want to take the inner product of x with itself, following the expression of inner product. That gives me x1, x1 plus x2, x2. And if I go further, I can have x1 squared plus s2 squared. Looking at what we have under the square root and my result here, which is the same thing as this, then it implies that norm x can actually be written in terms of but I'm going to be writing this way now. So this is the major relationship between inner product and norm. Now let's define a norm. Now recall that I said if you are defining anything here, you must consider vector space, because whatever we are building on the vector space. So now let V be a vector space over R or C. A norm is a function and that function is defined as this. It takes V to R or C. That is it. So is a norm and is a function. A norm is a function that takes V to R. For all x that we'll be considering later are members, x and y now, they are members of V. And I have also a scalar. We are considering a scalar based on the properties now. And scalar, let's say alpha. And f now, that is the function, must satisfy the following. 1. The norm of a vector x must be greater than or equals to 0. Norm of x is equal to 0 if and only if the vector is 0. The second property is the scalar multiplication. That is, if we have the norm of a scalar multiplied by a vector, the result is the same thing as multiplying the norm of that vector by the scalar. Then the third property is that it's called the triangular inequality. The addition of two vectors, when you take the norm, it is usually less than or equal to the norm of one of the vector plus the norm of the other vector. So if these three properties are satisfied by this function defined using norm, then it is called a normed space. What about inner space? The same thing here, we are considering two vectors. You say let V be a vector space over R, or it can be over C, whichever one you pick. Now, this is V. So now, an inner product, please take note of this, inner product spaces. So an inner product is a function as well, but this is how the function is defined. This is an inner product that takes V, combine V to R. It takes two vectors to R or C. Takes two vectors to R or C. Considering for all x, y, even z are members of vector V. And let's consider two scalars. Let's say alpha and me. So now, the following F must satisfy the following property. The first property is the symmetric property or the conjugate symmetry. It means the inner product of y must be the same thing as y, the inner product of y, comma x. For real, for complex, this will have a bar, which means this and this are equal. The second property is that of the linearity. Let's say this has a scalar multiplied by a vector plus another scalar multiplied by a vector, and you are taking the inner product of this with another vector z. Your result will be, let me do it a step at a time now. Your result will be something like this: alpha x combined with z plus mu y combined with z. So if you simplify this, you must be able to factor, that's linearity, you must be able to factor the alpha out, that is the scalar, and this as well must give you this. So if this and this are the same, then you can say the property is satisfied. That's the linearity. Then number 3 is that of this, the inner product of x with itself. We call it positive definiteness, which means that the inner product of x with itself is greater than or equals to 0. And if x is equal to, when x is equal to, and when the inner product of x with itself is equal to 0, it can only happen if and only if the vector is 0. So if you have those 3 properties, then the inner product species has been defined. So now, let's talk about the Banach space. A Banach space is a complete normed space. Very short. A Banach space is a normed space that is complete. What does that mean? It means that you define a normed space with 3 properties and include one more property to it. That's completeness property. So it means if you have a normed space and it satisfies the completeness property, it is automatically a Banach space. So let's do that. If you want to define a Banach space, you already know the definition of a normed space. Everything begins with let V be a vector space over R or C. A function this is defined as V taken to R or C for all x, y are members of V, and alpha is a scalar quantity. So now, norm must satisfy the following. The first property, norm x must be greater than or equals to 0. When norm x is equal to 0, x is equal to 0. Now, the second property, the scalar multiplication. When you have something like this, is equal to this. That's the second property. Then the third property is the triangular inequality. This is a norm. This is a norm. Now, if this property is now added, that it is complete space, it is a complete space. That is, every Cauchy sequence in V, that is in vector space V, converges to a limit that is also in V. So if this is what you have written, don't forget, you can add here that Banach space is a function this. Are you getting it now? That satisfy the following properties. That's the 4 properties. So if you have listed these 4 properties, you are talking about Banach space. So Banach space is talking about a norm space that has a completeness property, that satisfies a completeness property. Then what about the Hilbert space? The Hilbert space now is now an inner product space that satisfies the completeness property. So I'm going to be giving you this to write on your own. You are going to define Hilbert space, drop it in the comment section. I want to see how far you have been following. Don't forget, Hilbert space is inner product space plus completeness. So all you need to do is you define the inner product spaces and then add the same completeness that we have here in it, and then you have Hilbert space. So take note that norm is talking about length, inner product is talking about angle, Banach space is talking about norm plus completeness, and Hilbert space is talking about inner product plus completeness. So the major difference between inner product and Hilbert space is that Hilbert space is complete, while inner product is not a complete space. The major difference between Banach space and Hilbert space is that Hilbert space uses inner product to define its own norm, while Banach space use the usual norm. So Hilbert space is a kind of Banach space. Are you getting that now? It's a special kind of Banach space. It uses norm too, but the norm is not the direct norm. It uses inner product to define its own norm. So this is the major difference. The norm X under Hilbert space is expressed as this. But under Banach, norm X is the same thing as this. And if you find this video helpful, click on the subscribe button, like this video, very important. You can drop your answer in the comment box, then share this video. Thank you.